So two with us and one in Canada. Unfortunately, the first speaker, Jamie Burr, wasn't able to come, obviously, due to the pandemic. But I want to thank the three of us, but sorry, more particularly Jamie, because he's up at 3:30 a.m. in Canada. So he accepted to do the presentation in the middle of the night. So thank you very much, Jamie, for doing that. Very unfortunate that you are not with us, but I guess it will be for next time. So the three speakers, I'm going just to quickly cite the topic and the title of the presentations. So Jamie will start with getting to the heart of trail running, examining the unique cardiovascular stress of ultra running. Then we'll move from the heart to the neuromuscular system with Caroline Nicol from Marseille, who is going to talk about delayed onset muscle soreness versus actual structural functional recovery after endurance running exercise, and especially the sex or the gender effect. And then the final speaker is Grégory Doucende from the Université of Perpignan in Font-Romeu. And then we'll switch to biomechanics, and particularly he will talk about ascending speed, how to evaluate this ascending speed and how to use it with trail runners. So very excited to hear those three presentations. And with no further ado, we are going to let you talk, Jamie. Thank you again for being here.
Okay, excellent. Well, good morning, everybody, and thank you for having me. I apologize that I can't be there as well. I really wanted to, and I've been looking forward to this and watching the trail races and stuff going on in Saint Etienne. So it's an exciting place to be with you all today. Such a great culture there, it seems. So today I'm going to start by talking about getting to the heart of trail running. And what I mean by that is we're going to talk about the cardiovascular system. And so today I'm hoping to present a basic overview of some of the stuff that we've looked at in my lab and sort of the perspective that we take. Just get that to go. Okay, so my name is Jamie Burr, and I am a researcher here in Canada. I'm in the University of Guelph right now, which is about 100 kilometers from Toronto. So this is what my lab looks like. I am a sports scientist and health researcher, so I sort of have one foot in each camp. I'm not sure how funding works in France, but in Canada, we don't get a lot of money like the US does to look at sports specifically. So we tend to look at those two things together, and I think you'll see that in the focus of my work that I talk about today. So I want to start off by giving you some idea about how we approach this and how I got into it. And whenever I give these talks, where I talk about potentially not good things about exercise, I always want to preface that by saying, I think exercise is good. Because we all know exercise is good for us, right? And I think this graph shows it well, that we know the more exercise that we do as exercise volume increases, the health benefit or the performance outputs, they tend to go up. But we can accept that that's probably to a point. There may be too much of a good thing. And so some of the work that we've looked at is what happens when people push too hard, whether that be through overtraining with too much volume or too much intensity, or maybe if we do an acute bout that is at the extreme end. Hence, we arrive at ultramarathon running. But just so that we're clear, I do believe, and the data supports that exercise, by and large, is going to be good for us. So if we look at the survival probability over somebody's lifespan, we can see that those who competed as elite athletes have a much higher chance of survival than those who competed at low level or no level at all. Conversely, if we look at the incidence of cardiovascular disease, we can see the red line at the top here. Those are the least fit people. So your chance of having a cardiovascular event is higher if you have lower cardiovascular fitness compared to higher. So we'll accept that to be generally true. So how do we look at cardiovascular health and what's our approach to these things? Well, today I'm going to talk about two bits in particular. We're going to talk about how the vasculature responds, because that's really where we started. So one way we can get at that is by looking at things like the structure, using pulse wave velocity or looking at the waveform shapes, so we can measure those at the wrist, or we can measure how quickly a pulse wave travels from the carotid to the femoral artery. That's going to tell us a whole lot about the state, the structure of that vasculature, and we can gain a lot of insight from that. Many of you are probably familiar with the idea of flow-mediated dilation as well. So I'd say this more gets us at function. So you can see here in the top, we're using an ultrasound and we inflate a cuff below that level, and then we stop blood flow for about 5 minutes. And when we let that flow go, what's going to happen is we'll see a big increase in blood flow coming through in the shear rate. So the red blood cells rubbing on the endothelium there, they're going to release nitric oxide, and that should lead to a dilation of the artery as the reactive hyperemic response happens. And that's going to tell us a lot about the health of the endothelium and what kind of state we're in. I'm not going to talk too much about it today, but we certainly pair these measures with a lot of echocardiographic images as well. And we can look at all sorts of fancy things now, like how the heart deforms and moves and twists and all that stuff. So let's start with some very simple background. What do we know about things like arterial stiffness, pulse wave velocity, and exercise? Well, if we look at the majority of studies done, this is looking at training studies, and it's saying, okay, what promotes less stiffness? Less stiffness is good. Okay, we want a compliant system. And we can see here that generally, studies would tell us that exercise is good and that it causes stiffening to be reduced. Okay. Now, while I believe this to be true, there are some examples that show we can overdo it. So things like wind gait exercise, for example, high intensity, even for a short duration, actually has the opposite effect in the short term. It can go up. If we look at resistance training, the evidence is a little bit less clear. So you can see here that in general, there are some studies that show stiffening may happen and some that show it will go away. And it seems to depend on how resistance training is done. So again, if we push the body really hard and we keep progressing that, we do see over time that a stiffening can occur. Now, if we remove that stimulus, it tends to go away. And I think that's an important backdrop against looking at what happens when we push the body really hard for a relatively long time in something like an ultramarathon. If we look at what happens with FMD in exercise, I'll summarize quite briefly here, but I'll say that better endothelial function leads to a greater FMD response. We accept that to be true, and that's why our measure works. We could probably replace that by saying more exercise training also leads to a greater FMD response to a point, until the vasculature adapts and it actually gets bigger and then just stays bigger because it can't actually dilate anymore. If we look at what happens when we acutely expose the body to exercise and the change in that, I don't want to get too far into this, but just to orient you here, this is what the ultrasound outputs would look like. So we can see we have flow going toward and away from our probe, and we can rate that as shear. So we have what we call antegrade and retrograde flow, and antegrade is going the way it should be, and retrograde is going the other way. So if we measure that and come up with what the change in flow-mediated dilation would be, we can see here if we do something passive, like we heat a limb, there's going to be no retrograde flow, so we get a big FMD response. If we start to make this into more quote-unquote real exercise, so hand grip exercise, we can see we get an increase in the retrograde flow, and thus the change in FMD goes down a little bit. And then we take it to big, large muscle mass, cyclic exercise, or this is showing cycling. We can see that, yes, indeed, shear goes up antegrade, but it also goes up retrograde. So even though the signal is getting greater, the overall FMD response is less. So when we think about something like running and running for many hours at a time, it makes us say, well, what's the overall change? So let's take us to the ultramarathon running research. Now that you know kind of how we approach this and where we came from, this was sort of what we had in mind when we did our first study. And one of the things we looked at was the inverse of stiffness. So what we'll call arterial compliance. And I'm perhaps showing how old I am because we tend not to use this measurement as much anymore, but the idea still stands. So we want greater compliance, okay? And we measured it with this thing here where we can strap it to the wrist and we can get a waveform in the brachial artery, and then we can understand what the shape of that waveform means. And what we found is when we looked at people who do a lot of ultramarathons, there seemed to be some differences. So while the numbers may not mean anything, I think if I compare this here, this is showing you in orange the large artery compliance of an ultramarathoner, and this was a physically active normative group that we compared to. And they were in far better shape than the ultramarathon runners that we had measured. And to give you some context, the ultramarathon runners essentially looked like sedentary controls. And that was rather puzzling to us. And so we looked at that a little bit deeper, and what we found was that those people who had less compliance tended to be the ones who ran longer distances in training. Now, that was self-report. They told us how much they did, their frequency, intensity, and duration. But it did sort of raise our eyebrows and say, well, we better look into this a little bit further, which is exactly what we did. So we then took these people and we had them do an ultramarathon. This particular one lasted between 20 and 40 hours. If you're familiar with the North American scene, it was actually the first time the Fat Dog was ever run. And this is a race through the Rocky Mountains. And what we saw when they came back was, particularly focusing on large artery compliance here, their compliance, though it didn't start at a particularly high level, it went down even more. That was rather concerning to us. So here we have this evidence that suggests a relatively low intensity, quite prolonged exercise. It tended to increase stiffness, which raised all sorts of questions about, like, when did this start? How long does it last? What does it mean? And if we know that stiffness is generally not predictive of good health, does that mean that this is a bad thing for us? Just because it happens in the short term doesn't necessarily mean that. Which led to sort of our next studies. And I really simplified this here, but I want to give you some insight into how we approach this. One of the challenges of doing ultramarathon or trail running research, as any researcher in the audience would know here, is that essentially what happens is we often measure these people and then we send them off into the woods or into the mountains for a couple days sometimes, and then they come back and we measure them to see how different they are. But it doesn't give us a lot of insight into what happened in between. So I actually did this work when I was a postdoc and I was living and working in Vancouver, British Columbia. And so this is UBC's campus. If you've never been, it's beautiful. I strongly encourage you to go check it out. But one of the cool things about this campus is that it's situated on this peninsula right out by the ocean, and there's all sorts of trails right in the middle of the city around it. And this gave us a unique opportunity to actually run a marathon in the city. We ran a 75K ultramarathon, and one of the things that we told participants was they had to come back to the lab repeatedly. So the course actually went out through the woods and then it came back in, and we stopped the race in the middle of the way and we took some measures and we said, great, keep going. So this was important so we could understand the time course of things that were happening, and also to avoid things like this. I don't want to get too far into this, but we quickly realized in some of our early research that we couldn't control what people were doing at all. And oftentimes they'd come back and say, like, oh yeah, I was high for a couple of hours in the middle of the night. We had no idea what that did to the cardiovascular system. We still have very little idea what that does to the cardiovascular system, but that's actually a focus of my group now as well. So what did we find? Well, we had them go out. We measured them first at rest and said, okay, what's your baseline stiffness? We had done prior to the race at VO2 max. We said, okay, after a short bout of pretty tough exercise, what happened? And then we measured them about halfway through at the end, and we measured them in recovery to figure out, when did this start? How long did it last? And long story short, we found that stiffness didn't occur. We didn't see these effects that we were expecting, which left us with a really important scientific question, which means, what are the findings? What do they mean in context? We were really befuddled by this. Where do we go? So let's recap what we think we know at this point. We see that those who do many ultramarathons, they may have a higher baseline stiffness, and it seemed to be related to the distance and intensity that they undertook in training. We see that a really challenging ultramarathon, it does seem to cause arterial stiffening. So big mountains, long period of running. Whereas if we do a slightly shorter, slightly flatter, less intense, we didn't see this stiffening happen. So we're left wondering, what's the difference between these? And at the time, our working theory is that maybe it has to do with running up and down hills. Maybe it's the eccentric loading that comes with true mountain running. So we looked at what existed out there to try and build this theory. And this caught our eye. This was a pretty interesting study where they took salmonella. I don't believe they actually rubbed raw chicken, but it gives very good visual. And they took the salmonella and they injected a typhi into participants. This was actually done with medical doctors in a hospital. And after this vaccination, they looked at what happened with the pulse wave velocity, the stiffness of the arteries. And they saw that there was a significant increase by almost 0.5 meter per second. So to give you some context, if that were to happen without reason, if that just happened at baseline, that would be about a 15% increased reduction or increased chance of cardiovascular disease in their lifetime. They also saw that the wave reflections and the shape of these waves, they decreased what we call the augmentation index. You don't want a high one. It decreased it by about 5%, which suggested there was a peripheral vasodilation happening. Perhaps most interesting to me was that if they gave participants an NSAID, an anti-inflammatory, nothing happened. So this seemed to be related to the inflammatory response that was occurring from the vaccination. If we look at the exercise data on what happens with eccentric exercise, there's a pretty interesting study where they were doing hack squats with participants, and they had them lifting more than they actually could lift. So 2 people would lift up the weight, it was at 110% of their maximum, and they'd essentially say, don't let it crush you, and they just kept dropping it on them repeatedly. So 6 sets, they were really pretty beat up. And I don't want to get too far into the muscle soreness. I know we're going to hear about that a little bit later, but I think it's important to see what happened here. You can see the control group maintained their isometric strength throughout, whereas the group that was eccentrically loaded, they lost strength, and that stayed depressed for a number of hours. And we can see that muscle soreness went up after the exercise, and it stayed up for 24, 48 hours, starting to return by 72. And perhaps most interesting to me is we see that carotid to femoral pulse wave velocity has increased. So it's going up by 24 hours with a peak at 48 hours. This also seems to line up pretty well with what we see in measures of inflammation. So here's CRP, and we can see that it's peaking at 24 hours as well, and still staying elevated by 48. So the authors concluded that there seems to be this unfavorable change in pulse wave velocity. They did have a fairly high baseline stiffness, but we still see a change of about 0.2 meters per second. Interestingly, this change in central artery stiffness from pulse wave velocity measures does seem to be associated with muscle damage and inflammation. So we started to wonder then, okay, well, what about runners? I mean, that's interesting in an eccentric model, but what happens if we actually expose people to this? So the first study we did was done on this very fancy treadmill, which you can tell I built myself to make it a downhill running treadmill. Didn't have a lot of money at the time. This was one of the first studies we ran. And we had participants come to the lab and run downhill at negative 12%. They ran for, it was 40 minutes at about 60% of VO2. If you've never had the pleasure of doing downhill running in this kind of a study, it's fun. It's pretty easy running in terms of the cardiovascular feel, but you turn into Bambi. You get like wobbly legs very, very quickly. And for the next few days, you can tell exactly who on campus was in the study. And what we showed from this is there was indeed an increase in pulse wave velocity. And we saw about 0.5 meters per second, and it peaked again at 24 to 48 hours. When we took that data and lined it up with changes in muscle soreness, we can see that there is a relationship between those. So those who showed the greatest stiffening also reported feeling the most sore. Okay, so this takes us to sort of the meat of what I'm going to talk about today, and kind of where we're at now. And I'm going to talk about a few studies that were all done at the Sulphur Springs. So this was a local race that we found here. And at the time, in trying to understand where we're at and what all this means, we realized there wasn't a lot of literature that looked at having people run the same course, having athletes do the same thing just for longer periods, where we control as many variables as possible in the real world setting. There is now a group in France who you may know, who is doing this very well, possibly better than we did. So some exciting data coming out of that, and I'm excited to hear more about it this afternoon. So what we did, though, is we had 4 race distances, so a rather short one, and 3 ultramarathons, 50, 80, and 160 kilometers. So we had participants all start the same course, and it just depended on how many loops of the course they did. So you can see here they ran day and night, the 160 kilometers going the longest, obviously. And the course was about a 20K loop, and it had 620 meters of elevation per loop. So what did we find? First thing I'm going to talk about here is our measures of pulse wave velocity. So we can see we did take blood samples from them because we were really interested in understanding, is this all about eccentric and inflammation? And you can see that in all of these groups, there was an effective time such that compared to baseline, all of the groups increased the amount of inflammation that they showed. There's more time in the longer races for that inflammation, that cascade to occur. And though not significant, there does seem to be a bit of a pattern here. If we look at changes in pulse wave velocity from the start to the end, a few things jump out to me. First of all, we see in the group that ran the shortest distance and the longest distance that there was actually a decrease in pulse wave velocity. And that's sort of what we would expect with just normal exercise. That was a little bit unexpected to us, but interesting to see. When we compare that to the middle 2 groups, the 50 and the 80 kilometer race, we can see that they didn't go down as normal exercise would, but it was actually sustained across that period. Let's try this is the same data, just presented in a different way. Interestingly, you can see there's a much more homogeneous response in the short and the long race. And we see this spread about the data here when we look at the individual data points. It's perhaps worth noting here that when we look at, well, what was the cardiovascular response in terms of the intensity of the exercise, and we measured this, we looked at this using heart rate and by using the time because we had laps and we could figure out the pace. You can see here that the percentage of the race made up of moderate intensity, it's the same basic period of time here, but we can see that it decreases as the race gets longer, and low intensity becomes a greater proportion. Not surprising. We know that people can't sustain a high intensity for a really, really long time. So longer races are run at a lower intensity. That may be affecting our pulse wave velocity measures. And we also looked at flow-mediated dilation. This was in our fancy RV motorhome lab that we had with us. And you can see here we actually did femoral measures as opposed to brachial, which are much more common. And we can see here that comparing across the race distances, there wasn't much of a change, again, in the shortest and the longest race. But in the middle here, it seems that there's a depression in FMD. Now, only the 50-kilometer race was a significant depression, but again, I think there's a bit of a pattern that starts to emerge here. So perhaps this has to do with the balance of intensity and duration. It seems that running hard for a relatively long time, let's be clear, even a 25-kilometer race for most people is not short. It seems to be that when you run relatively hard for a relatively long time, that's when these changes start to occur. So why do we care about this? Well, certainly I think it's important to understand this from a health perspective. What does this mean for people in the short term? What does it mean in the long term? And we're still working to figure that out. But from a performance perspective, I think it matters as well. I don't want to get into the real specifics of this, but this is looking at changes in the heart. So changes in tissue velocity and deformation. And really what I'm showing you here is that this is one of the first studies we did again, so we're still using compliance here. But we can see that those who had greater stiffness or less compliance at baseline tended to show the greatest changes in these measures of the heart. So cardiac fatigue was a bigger problem in those who had stiffer arteries. More recently in our lab, we've also shown that there are changes to cardiac output from overtraining. So specifically trying to make people do a little bit too much, we can see that stroke volume, for example, tends to drop off. Cardiac output tends to drop off over that same period. And at the same time, we can see that pulse wave velocity is going up. Looking at measures of sympathetic output and stuff, we can see that it is driven through the sympathetic side. So this overload does have effects that could affect performance, and it may have effects on health over time. The last thing I want to talk about this morning is looking at predictors of race performance. So we did all of these at the same time. And since we were taking all these measures on people before and after the race, we thought, this is an opportunity to also understand what is it that tells us who's going to be good, who's going to perform well based on their baseline data. So we did a training history questionnaire. We asked them about how often do you run, what kind of strength training do you do, what's your experience, how many marathons or ultramarathons have you done, and your weekly kilometers. We had everybody join us in the month before the race to come in and do a VO2 max, do running economy. We looked at caloric cost and oxygen cost, and we looked at the velocity at their VO2 max. We took general measures of cardiovascular health, so things like resting blood pressure and heart rate. We looked at body composition, how old they were, and we tracked them throughout the race to figure out what were their changes in their body weight. And we also looked at blood measures to figure out how hematocrit and plasma volume changed as well. So I'm going to try to blow your mind here with some results, particularly this first one. One of the things we found was that those who trained more seemed to be better. Shocking, right? But it did depend on what race we were talking about. So I'll just orient you here really quickly. This is showing performance as relative to the race winner. So the race winner would be 0% different from themselves because they won. And as we move this way, that means they were that much slower than the race winner. So we can see here in training volume, for example, those who did the most training tended to, at least in the 50 kilometers for men and the 50 kilometers for women, they tended to perform the best. Interestingly, though, we can see here that in like the 80 and there's our 160, we don't see the same pattern. So as the race got longer, that became less of a factor. We'll just jump over here because I think it's another obvious one. We can see that those resting heart rates that were lower tended to be better. So I'd suggest that's probably because they were more fit. And we can see here that that, again, holds for the 50 for the men and the women, but the effect isn't as great for the longer races. And I'll just jump through this a little bit quicker. We can see mean arterial pressure, only significant for the men at the 50K, and we don't see that pattern hold here, for example, in the 80 kilometer. And when we look at measures of body composition, which may also tell us something about training and experience, we can see that this held for the 50K men as well. When we look at the measures we've been talking about here, so pulse wave velocity, for example, we can see that those who had the, I'm sorry, peak velocity is what I meant to say here. Those who ran the fastest, had the fastest speed during the VO2 max, they tended to perform the best across most of these race distances. And finally, when we look at body mass, we can see that those who had the greatest losses in body mass tended to do the best, at least in the shorter races. And I'm going to come back to that. So what did we see here? Aside from looking at those, which I just kind of rushed through, I hope you're able to pick that up, those individual markers, we also put this into multi-regression modeling. And so we looked at this and said, okay, what were the things that predicted success at the 50K race? So you can see here that it's a fairly good fitting model. And the things that predicted it were, what was the percent change in body mass? How much weight did they lose across the race? What was their body comp beginning? How old were they? Resting heart rate, perhaps that's indicative of fitness, and their mean arterial pressure. When we look at this percent change in body mass, I found this rather interesting. We can see here that in all the race groups, including those who didn't finish, there was a decrease in body mass. So generally, people lost weight, probably because of plasma losses. Interestingly here, though, we can see that we would expect hemoconcentration. If you're losing plasma, there should be more thick stuff left in the blood. And that was true in most of these. Those who didn't finish the race had the greatest losses, so perhaps that was insufficient hydration. But in this group here, the 80-kilometer race, for example, we actually see the reverse happening. So they were not seeing hemoconcentration, it was hemodilution, which is an interesting idea that perhaps there's something going on here. Could be that they were hydrating in a different way, though we did see losses in body mass. So this may mean there are some kind of fluid shifts that are occurring here. When we look at the 80-kilometer race, again, the model fits fairly well overall, but we can see that the only thing that was predictive of success at the 80-kilometer race was actually running fast in the VO2 max test. So those who could run fast, ran fast. And when we look at the longest race that we had, there were no physiological predictors of performance. The last thing I want to touch on here briefly, we were very interested in understanding sex differences. And honestly, we wish we could have dug into this a little bit more, but we only had enough female representation in the 50K race. And so what was it that drove this here? Well, we can see if we split it into men and women, we still have a pretty good fit in both of these models, but it is slightly different. So the peak speed at the VO2 max test was predictive in both of these. But beyond that, then there was a change. So in the men, it was their mean arterial pressure at rest. And in women, it was actually how much fluid was lost. And you can see that's really what was driving this 50K model. So lots of work to do to understand that a little bit further. But let me summarize what I just told you about performance. So we see that the classic determinants of running, so being young, having good cardiovascular health, being fit, those tend to influence the shorter races, in our case, the 50K ultramarathon. Longer distances are less influenced by the same things, and they're mainly driven by running fitness. And then when we look at the longest distance, the 160K, it must be dictated by something else, perhaps psychology, perhaps something else we're going to learn about in the next little while. But we didn't see anything there. So with that, thank you for your attention. I'm happy to answer questions, and I want to just recognize my group that does all the hard work.
Okay, thank you very much, Jamie, for this very nice presentation. I think we can have a general discussion at the end, but we'll take a couple of questions for now. If there is any burning question, we can take some. We have a couple of minutes for that. Any question? Yeah, Giorgio.
Thank you. Can you hear me? Actually, okay, perfect. I have just one short question about the main results of the second part. So that classic index of performance affect just apparently short, if you can call short, 50K distances. And I wonder how this can be related to the participation at your trail running race, because maybe stronger athletes or younger athletes, which is what I thought, younger athletes who possess greater VO2 max, etc., maybe participated to the shorter competition because it's closer, because yeah, maybe they don't have the experience to stay outside for 30 hours, etc. Just yeah.
Yes, great question and insightful thought. I'll tell you one of the things that surprised me, and perhaps this is obvious to a group like yourselves. When I first got into this research, I sort of expected that, I knew what a marathon runner looked like, right? Compared to most people, they're very fit. They have high VO2 maxes. And the first time we tested the ultramarathon group, I went, well, they're going to be like super marathoners, right? Because they do ultra marathon. So I'm expecting, VO2 is up in the 80s and all this kind of stuff. That's not necessarily the case. We don't always see that. And to your point, like, is there a selection going on here? What I think we saw in our group was that those who ran the longer distances, absolutely, they had more experience. In our case, they actually tended to be a little bit more fit on whole. We did have a few runners that did the shorter races at a very high intensity and were quite fit. We had some Olympians that came out and joined us. But for the most part, I do think that that is an interesting observation. And that is true, that there could be some selection bias. And those who are older and more experienced, it may be mental, it may be physiological, but they were just able to handle the longer races and actually do that and complete it without dropping out. If we look at the data for those who had to drop out, they tended to be, they didn't hydrate as well as I showed you, and they also weren't as prepared. So if we looked at their training in the month leading up, it was not as well-rounded. So I think you're absolutely correct that there is something going on with who those people are.
Was there a significant difference in terms of age?
We did tend to see that there were older people in the longer races, and I think that's probably a factor of experience. Experience is easier to accrue over a longer period of time. So yes, there were some younger people in the short group.
I'm trying to remember if there was a difference in our UTMB study in terms of age. No difference for us. Okay. Any other question? We have time for another one. Yeah, Gregory?
Hey, Jamie. Thanks a lot for the presentation. I just have a question because on my study on cardiac fatigue in Ironman and also ultramarathon trail running, we also observed U effect on the fatigue with on Ironman on 15 hours of duration. There is a lot of cardiac fatigue on strain and torsion and twist. But when we test it on ultramarathon like UTMB, we don't have any fatigue on the urge. And you have the same results on vascular system. So I have just a question. What was the duration of 50 kilometers and 80 kilometers and the ultramarathon of your race?
Yeah, great question. And I'd be happy to chat about cardiac fatigue and kind of where we're going with all that stuff. I'm going to be honest with you, off the top of my head, I don't really remember. I want to say the 160 kilometer race took 25 hours. But I'll tell you what, I can go back and get that information for you. I think you touched on something really important there. When we looked at our measures of cardiac fatigue, it does seem to be intensity dependent. And so there may be this interesting idea that you can kind of just keep going for a long period of time, and that's fine, depending on how stressful that time is. So we're actually undertaking some cardiac fatigue studies right now in the lab, and we're actually adding to, so we're doing a couple of hours of exercise, and then we're putting in a number of wind gates on top of that to determine if that's actually the stress that causes it. And we're looking at the same measures you just mentioned there, so torsion and strain and all that kind of stuff. So TBD in our hands. But the one other thing I'll point out is that we gathered some information that shows it might also have to do with the way we measure these things. So typically, as I said, we collect these runners at the end, and they don't want to exercise anymore, and so we lay them on a table and we take these measures. We found that if we add even a light cardiovascular stress with stress echocardiography, that some of these measures that have been reported repeatedly to not occur after some of these events, they start to present themselves again. So we're quite interested in following that up as well.
Okay, great, thank you. If there is no further question, I think we'll stop here for now and switch to the next presentation where I guess we'll keep talking about eccentric and inflammation, but the effects on the neuromuscular system now. Before I give the mic to Caroline, I would like to say to people on YouTube, if there are any, that there will be if you're interested by the second part of your presentation, Jamie, on determining factors of performance, we'll have the PhD defense of Frédéric Sabater at 2 p.m. French time this afternoon. And I know you know that because you're in the committee, but please attend if you can. Okay. And I also take the opportunity to thank Thibaut Besson, Rodolphe Testa, and Bruno Schiterio for helping with the technical aspects, which seems easy, but I can tell you that it's not that easy. So thank you, Thibaut, for doing that. Caro?
Thank you, Professor Guillaume. Thanks, Professor Burr, for such a nice talk. It's my pleasure to be in here. Nice day. Have a nice day to all of those who are listening to, who are present. And I would like to say that I'm quite touched today to be here because almost 30 years ago, I was celebrating my own PhD in here. Carmelo Bosco was doing it as well because he had to pass a second PhD under the supervision of Paavo Komi that you can see at the end there. And no, this does not work. And you can recognize Alain Belli, Pierre Marconnet, and of course there was Jean-René Lacour and André Gessin. So it's nice to be here in Saint-Etienne. And for those who are just away, welcome to this nice, beautiful lab in here. So let's move to the talk. As said, Professor Guillaume, I will be discussing about the delayed onset muscle soreness versus the actual structural functional recovery after endurance running exercise, giving some last results about any gender effect or sex effect, as he said. And I'm sorry, as I'm interested in DOMS sensations, I'm mostly dealing with recreational runners more than elite trail runners. So I will try to make links with trail in order to be within this topic today. So I will start by providing some basics about the stretch-shortening cycle, the way that muscle functions in most ground locomotions. And then I will come to the fatigue it induces, its time evolution, and some of the underlying mechanisms. Then we will get to these origins of the delayed onset muscle soreness and its time evolution as compared to the actual functional recovery. And I will end up with recent studies performed by the PhD student, Robin Mackie, that I'm co-directing with Fabrice Vercresson, who will be in the jury this afternoon. As you can see, his topic is really close to mine today, because he's working on the structural functional recovery pattern of male and female recreational runners. And we are not dealing with trails, but as you can see, we are interested in muscle, in the muscle fatigue induced by Marseille-Cassis race. You don't know this race for some of you. It's really interesting because there are more than 35% women taking part every year. And this 20-kilometer race, which is so short as compared to all what you spoke about just previously, is interesting because it includes small increase, a small gradient, only 300 meters upwards and then downwards. But for recreational runners, this is far to be enough to induce both acute and delayed muscle fatigue. And this is what I will be talking about in the last part of the talk. But as said Professor Millet this afternoon, there will be a PhD, but a few weeks ago, there was a nice PhD by Thibaut Besson that you can listen on the same tube. And we are hoping to be all getting one review paper on the female endurance runners. And there will be this nice PhD on trail versus road runners that I'm just waiting for in the afternoon. So let's move on. if I go back to the basics, so running belongs to these so-called stretching type muscle actions. And when you look at this vertical ground reaction force, pointer doesn't work, but you can see it, it's the upper curve. You can see that we are repeatedly facing ground impact peaks of 2 to 4 times body weight. To face such impacts, lower limb extensor muscles such as the gastrocnemius, but also soleus for sure, the vasty muscles are optimally preactivated prior to ground impact. Then they will be fully activated during the subsequent braking phase in order to resist to the induced hip, knee, and ankle joint flexions. This will, bless you. This work, I want to say it, is not eccentric in all muscles. Biarticular muscles will not be working eccentrically. They will be either working concentrically or isometrically. And if it's sure that the soleus will be stretched, the vasty muscle is not even sure for them. So let's be careful to speak about braking phase and not eccentric phase. Anyway, this active resistance to stretch of the muscle tendon unit allows it to store elastic energy, energy that will be recoil during the subsequent push-off phase if the transition between the braking and the push-off phase remains short, and this is important. Then, if it is short, you can see in here that the vertical and the horizontal forces are produced at fairly low EMG activity, which makes the SSE fairly economical, what is interesting in endurance locomotion. The problem is, if I switch then to trail and all what I've been watching on those different pictures and videos of UTMB, is that for sure you may be facing ground contacts which are not on flat terrain and not on hard soil, so that then you will be losing this elastic energy when you are running on the snow or in the water, and this will then require much more work during the final push-off phase, which is fully concentric work and then fairly costful. So there will be an increase of the rate of passive exertion, and this will be the vicious circle leading to these fatigue effects. Furthermore, if we look now in trail running at the influence of the positive and negative gradient, you have in the middle the normal ground impact peak. If you are running downwards, you can see that this ground impact peak is increasing a lot. When you are running upwards, it's almost disappearing, because in downhill you will increase the braking work, whereas in the uphill you will be increasing the push-off phase work, which means that then it will become much more costful. That's why I make a jump to a graph that will be presented this afternoon, which is really well known from Monnet, and it's interesting to think that the SSE is roughly well efficient in this flat terrain or slight downhill, whereas when you are running upwards, you are increasing the concentric work, and then thus the running cost is clearly increasing. On the other hand, when you are running downwards, you are increasing the braking phase. If you start working more and more eccentrically, anyway, this is much less costful than the concentric, because you have this resistance. I will make it. The elastic resistance from the muscle and the tendon that are just cost less. So let's come back to the SSE. One important thing maybe at low and moderate speeds, that you may have the intervention of the short latency stretch reflex. And this stretch reflex loop will take place at the early braking phase, which makes that you will get an increase of the muscle tendon resistance, resistant to stretch. Its stiffness will increase, thus will allow more elastic energy to be stored and recoiled during the subsequent push-off phase. This is not working so well at high speeds, and it's important to say it. I'm speaking about the about the stretch reflex, because you will see later on that fatigue may disturb this. So let's go to fatigue. Guillaume has been working so much on all kinds of exercises. I've done some as well. So if we combine these quickly, you have all kinds of exercises that have been studied. They have been of different types, either continuous, intermittent, on ergometers or on the real surfaces. And so I will try to show you the original ones, because Guillaume asked me to speak about old stuff. So as planned, I do. In 1988, there was one study of Alain Belli in here on endurance runners, and I discovered in here the Douglas bag, and they use, you don't know what it is, but at that time that was just excellent, good. And I was on my way to Finland. And then when I came back for my PhD, so we made it in Nice, and you can see on the upper left side slide that at that time we didn't have K4 and K5. It was quite complicated to record VO2 on the ground during the treadmill, during the run, sorry. In that experiment, we had 8 people, but 7 males, only 1 female. She was a triathlete and made really nicely the job. There were 7 males who were marathon runners or trailers, not trailers, sorry, triathletes as well. They had to perform an experimental marathon, and then every 10 kilometers, they had to run on the track with these measurements. Then they had to perform maximal sprint. And at the end, they had to make all kinds of tests, plus treadmill runs, as you will see later. So what showed us these progressive sprints performed every 10 kilometers? You can see on this graph that there was a clear increase in the total contact time, braking, push-off time. You can see a clear deterioration of the vertical ground reaction force, showing a drop in force right after impact, so loss of tolerance to ground impact, leading to a deterioration of the strengthening cycle and much longer components. So clearly, the performance declined along the marathon. At the end of the race, we had some other types of SSE tests. And what is interesting is that when you look at these results, pre-post fatigue, in sprint, file jumps, drop jump, counter movement jump, what is clearly seen is that only those tests that had ground impacts showed declines in performances after the marathon. The counter movement jump, which is maximum but without ground impact, was performed more slowly, but most of the people even improved their performance. So we have to be careful with this type of test to so-called examine the fatigue after endurance races. What about the treadmill running test? We were testing them at 3 different velocities that remain the same, of course, before and after the race. And you can see on this graph in here that there was absolutely no change in here, no change in either braking, push-off, or contact time at any of those velocities. You can see on the upper graph in here that the knee angle versus hip angles during the contact and during the flight phase remain also really similar. But this occurred because behind there were clear neural compensations. And those neural compensations did not occur during the pre-activation phase, but there were clear increases during the braking and during the push-off phases. And the faster they were running, the more compensations we could see. And I would like to show you also this. When you see that there were increases in EMG, no changes in kinematics. Sorry. This again. Sorry for that. I clicked on the wrong button in here. So I can keep on saying anyway, that there was absolutely no relationship between the kinematic changes and the running economy ones. And that will not surprise everybody, and it has been quite often the case. But what is nice also is that the only woman, she was the one in here. When she ended up the race, she had lost 56% of her maximal knee extension torque. And this woman was able to run at the 3 speeds on the treadmill. But look how she did it. She was collapsing after heel contact, flexing really much the knee, losing a lot of time during the braking and push-off phase. So her feet stayed so long on the treadmill that she had to move it back forward along the treadmill belt in no time. But that way she could run on the treadmill. This would have been impossible on the track. So let's be careful when we use treadmill to measure fatigue also. Anyway, Paravokomi said, okay, it's nice to have complex measurements on the field, but let's move more efficiently in a Finnish way. So he invented this sledge apparatus, which makes that in few tenths of minutes, you manage to kill the muscles that you want on one leg, on the other, on both. You can choose the angle and the way you will be fatiguing more or less the muscles. So that's the way the SSE fatigue has been mostly studied in the literature. So let's look at those results. When we look at the functional recovery after prolonged SSE exercises, so including these rebound exercises, those have been mostly studied in men. And you can see that usually we observe a biphasic type recovery. What do I mean by this? Is that this starts by large acute deficits in maximal static dynamic force, as well as in maximal voluntary activation, EMG activity, stretch reflex EMG response. But what is fairly interesting is that in many participants, you can observe a partial or total recovery within 2 hours. And then you will get these large secondary deficits again, 1 or 2 days later, usually associated with delayed onset muscle soreness, and this will slowly by slowly disappear along the subsequent days. So I spoke about the stretch reflexes. Look what happened. Because this, we have been studying it a lot, and I don't think that it has been done much in trail runners. We studied this a lot in passive stretch condition, in active stretch condition. And what is quite interesting is, first, you see this biphasic recovering pattern. But when you see the disappearance in here of this stretch reflex intervention at the beginning of the impact, it's quite nicely related to the drop in force after the impact peak. That means it's also related to the deterioration of the SSE efficacy, leading to this prolonged push-off phase, which is really costful. So I think it could be interesting, perhaps, as a parameter to study. What about the proprioceptive disturbances that we observed 1 or 2 days later? If you have sore tricepsurae and you perform large dorsiflexion, what you can see is that there will be an overestimation of the angle that you reached. You all know this. If you are skiing and you have sore quadriceps, you will feel much more flexed than you are. And when we tested by vibrations, tendon vibrations, the sensitivity to movement, it was on the opposite, fairly lower. So this has been considered in at least downhill skiing as potentially leading to muscle injuries or joint injuries. And I don't know if there are any types of research on that topic in trail runners. So what are the underlying mechanisms of this biphasic functional recovery? It's quite challenging. We may be wondering about the influence of muscle damage that Professor Burr mentioned just before, the influence of physiological fatigue, or the influence of the neural adjustments to both of these types of disturbances. So referring to the ultrastructural muscle damage, I would like to emphasize in here that we always speak about them, although there are so few real indications of damage in the literature. There are so few papers, among which this one of Warhol in 1985, where they have been finally making repeated muscle biopsies to quantify those damages. And even in this paper, he found that in the most severe cases, there were less than 10% of the sarcomeres which were damaged. If you know the size of a sarcomere, you need the microscope to see those damages. So when we speak about muscle damage, let's think how little they are. Second thing, when we consider those damages, if they would be so big, how would we explain the partial to total recovery we have 2 hours later? They can't recover in 2 hours. So if we have to move on, at least for the acute phase, to the other possibilities, of course, you have the physiological fatigue and all those parameters which are likely to affect or contribute to the acute fatigue effects. A third hypothesis is quite interesting as well, because when you look at the metabolic parameters in here, metabolic changes, the increase in muscle temperature, the increase of plasma within the muscle, and thus the tension inside the muscle, all these chemical, thermal, and pressure stimuli are likely to stimulate muscle afferents, including the 3 and 4 ones. And these will be then influencing the central nervous system, not only at the spinal level, but also at the supraspinal level, and thus influencing the entire neural command. What is also fairly interesting is that those afferences have been shown not only to induce protective, which means inhibitions of the fatigued muscle, but also compensatory ones, pushing further the muscle to fight against fatigue. So, sorry. They may be as well involved in DOMS, and that's what I will be showing you now. So, so if we look now at the way these neural changes could be taking place or influencing the force drop that we have been observing quite often, you can see that in 15 of these 16 studies that we looked at, there were clear decreases in both surface EMG activity and maximal voluntary contraction. From those which studied the entire functional recovery pattern, you can see that there were again changes in both neural command and the functional output as well. So emphasizing the potential EMG influence on what was observed on the force output. Voluntary activation has been also shown to be showing biphasic decreases. I would like to come back to what I said earlier, that the metabolic fatigue may be explaining more than the muscle damage, the acute drops in force and in EMG. What we did at that time is that we performed intermittent SSE exercise to limit the metabolic fatigue, but thus to allow more muscle work to be performed. And this resulted then in much lesser drops in both maximal EMG and force in the acute phase, and much larger decrements in the delayed one, showing that it's not muscle damage that could be explaining what we observed in the acute phase, and it's not at all the same type of fatigue in the acute and delayed recovery phases. So if we look at the underlying mechanisms that I hope you will be following here, in the acute phase, it's quite common to be measuring lactate, although we know that it has nothing to do with the fatigue. at least is not one parameter inducing it. There are peaks of interleukin-6, prostaglandin a bit later, 2 hours later, leukocytes as well. But what is interesting is that each of these parameters is known to be sensitizing 3 and 4 muscle afferences that may then influence the central neural command at both spinal and supraspinal level, leading to neural protection of the fatigued muscle. In the delayed recovery phase, you will see, as you mentioned it, Professor Burr, indirect markers of muscle damage. And I would like to emphasize there are indirect markers. They are known to be not at all in proportion with the amount of damage. And it just happened that they are delayed, measured in the blood, but there are also problems with this. Anyway, serum CK and these C-reactive proteins may occur and show peaks 2 days later, as well as the muscle thickness, which is increased because plasma is getting inside the muscle to recover the damaged muscle fibers. And then you will have all those stimuli I spoke about earlier that will be leading to adjustments of the neural command. Why do I say adjustments? It's because they are fully different depending on the testing tasks you are using. In maximal drop jump, we are systematically seeing inhibitions in the pre-activation, braking phase, sometimes even in the push-off phase, in the central command, in the reflex command. Everything is just protection. So people will be absorbing the shock. But what I like is that at the same time, if you ask people to perform a submaximal rebound exercise, then you may see all kinds of different adjustments, which vary depending on the SSC phase and vary depending on the acute and delayed recovery phase. Remember, in these intermittent SSC studies, we managed to have only slight drops in force right after the exercise. And in this case, what you can see in here is that people could keep on rebound by pre-activating more, activating more during the braking phase, and there was no change in stretch reflex. What happened when they were much more fatigued 2 days later? It was completely different adjustments. Then we had an increase in pre-activation, but there was absolutely no change in EMG during the braking phase, no change or even a decrease in the stretch reflex, so that the shock was absorbed. And then, of course, to rebound, they needed to activate much more during the push-off phase. So you see that there may be neural adjustments which are SSC phase dependent and depending on the amount of fatigue you got at a given time. So what about delayed onset muscle soreness? I guess that I will go quickly on this because everybody knows this delayed rise in muscle soreness, the hyperalgesia, and the early drop in soreness. What I would like to tell you is what leads to these DOMS. It's not simply damage. It's not simply inflammation. It's because 10 to 15% of these 3 and 4 muscle afferents only are nociceptive, which means that when the inflammatory soup, what we call, is developing, when the inflammation gets bigger and bigger, then when you are approaching the peak of the inflammation, then only you feel the DOMS. That's why they come late. But in the same way, it's only when you are around the peak of the inflammation that you feel sore, which means that when you pass this peak, soreness will disappear before the actual functional recovery. So inhibitions may still be there when you don't feel soreness anymore. You should not trust the disappearance of DOMS to say, well, I recovered. And I hope this is clear. We have also to be careful when we speak about runners because they want to start running all the time and restart running all the time as soon as possible. The thing is that when they go back to run, they will have again increase in muscle temperature, chemicals, increase in pressure. But those stimuli in here, which are abnormal when you stand up in the morning, they are completely normal once you are running, which means that DOMS disappear when people warm up, when they start running. And they say, well, that's the best way to recover from my muscles. No, it kills the soreness because the stimuli are normal, but it doesn't mean that you are recovering. It doesn't mean you don't have inhibitions. It doesn't mean it's safe. So the real danger, if I would say, is it when you feel soreness or when it gets away? I would say if there is something to tell to people is really this. Let's be careful when DOMS disappear because you start moving or because you just start recovering. This little DOMS is the danger. So we finally get to these gender or sex differences. And this is the work of Robamaki. I would like to go fairly quickly on this. He made a nice publication in 2020. It's nice to say it's a nice publication, isn't it? So he had tests. He was testing 10 men and 10 women before Marseille-Cassis race, 30 minutes after, 2 hours later, then at the peak inflammatory on 2 days, and at 4 days in order to be after the peak. He used maximal voluntary contraction, squat jump, drop jump, and a force velocity test, but this one only in the delayed recovery phase. To summarize his results, what is clear is that he found, like, as you can see in here, larger decreases in knee maximal voluntary contraction in men than in women, which is quite often the case, and we can discuss later about this. What is interesting is that in drop jump, only males showed delayed decrements in performance or in different parameters when women had none. Squat jump, as you expected, no change, and women learned the task. And on the force velocity test, only men showed a drop in maximal V0. This is a theoretical value, and a drop in the maximal power 2 days later. Women had already recovered. So women seem from that first study to be less fatigable or to recover faster than men. And this fits fairly nicely with this well-known graph of Hunter and collaborators showing that when you have women, they are usually showing larger proportion of slow twitch fibers, leading to lesser metabolites. They have lesser muscle mass, leading to the same thing. Those will be then leading to less sensitization of group 3 and 4 muscle afferences and less influence on the neural command. So the metabolic fatigue could be lesser. Estrogen are also protecting the muscles and guiding the inflammatory process. But what I would like to say in here, because in trail that may be interesting, only our recreational women runners reported DOMS in the hamstring muscle groups. And when we asked them, they already felt those during the last downhill part of the race, when they had been well fatigued by the uphill run, and then this part was really at the end of it. And at that time, when you know the greater laxity of the knee joint of the women, you can think that they were not only holding their knee with the quadriceps, but also with the hamstring muscle group. And the problem is that then, oh, sorry, you don't see in here this graph, but then they may be getting stiffer lower limb at impact, increasing the impact peak, and then leading to greater loss of tolerance to ground impact and further stretch of the muscle. So this, we have to further look at it. On the final slides about the force velocity test, what I would like to say, because This will be getting out, I hope, pretty soon in a publication. That men and women use differently their muscles in this multi-joint push-off. And what is quite interesting to see is that when women use mostly the quadriceps during the push, you see in here those pink curves. Let's take this one, using much the vasti and the rectus femoris. They use much less the hamstring muscles. Whereas when you look at the men making the same push, they are using the hamstrings at the same time at the knee, than the knee extensors. So hip extensors and knee extensors when women use the hip much later. And with fatigue, what we could see is that the vastus medialis was the one that was the most affected for both men and women. And I won't be telling you all those informations about the synergies. This push could be subdivided into 3 synergies of all muscles in both men and women. But what was interesting is that only men showed for the first and the second motor primitives that the center of this activation occurred later on day 2 and came back to normal on day 4, occurred later on day 2 and came back on day 4. So these muscle synergies and the center of activity of these synergies might be a new way to be studying in complex multi-muscle and joint work altogether, the way there could be different strategies used during fatigue. So I would like to finish saying that we just ended up a new study to follow not only the functional recovering pattern, but also the structural recovery pattern. So as we did not make biopsies, we use MRI to follow before and 2 days and 4 days later, or 1 day and 3 days later, the evolution in all the muscles of one lower limb. And we used at the same time ultrasonography on all those muscles to see if ultrasound could be used in the future to follow the structural recovery. But as this experiment ended up just 2 weeks earlier, I can't show you those results yet. So I'm really sorry, but what may be of interest for you is that we put them also on the alter G to modulate the gravity forces, and it seems that we could see disturbances there, and that could be a nice tool we use on trail runners, in my opinion, to see how they may be able to still detect or not changes in external forces. We use some maximal and maximal rebounds in order to show those neural adjustments I told you before. So if I did not make you fatigue, I hope that you can still be able to read this by yourself. It's big enough. And I thank you for your attention.
Okay. And thank you also for showing that there was actually for the young people in the room, there was actually science 35 years ago, as you can see. So it didn't start two years ago. It started before that. No, very interesting. Thank you very much. I think we have time for a couple of questions, and then we can. I think we said until 11:30. So, and I believe Grégoire, your presentation is a bit shorter, so we're good. So we can take a couple of questions. I have some, but please go ahead. Ready? Okay. So, Caroline, I have a couple of questions for you. I thought that Thibaut will have a question for you because I know at least he should have one. So Alexandre is here. So at some point you the third part when you talk about the dumps and you said something like, this is where the real danger is. I guess you were thinking about, okay, you have no pain anymore, but you're still functionally depressed. So do you think it could be at this moment, when you talk about danger, what did you mean by danger? Danger of like getting injured or?
Thanks for your question. I think that's the only thing to be careful with dumps. Those damages are so small, no big problem. You saw that we get inhibitions. When people feel sore, they are careful. Let's speak about those who are skiing. They reduce their skiing distance. They go to have nice coffee or hot drink. I don't know for trail runners if they can make a stop, but in any case, they are careful when they feel dumps. The problem is that when the dumps disappear, everybody feels Superman, Superwoman. You say, yes, now I get the repeated bout effect. I have stronger muscles. I'm better equipped in my way to activate even those muscles. I'm better. The problem is when dumps disappears, it doesn't mean indeed that you have recovered. And the more dumps you have had, the worse and the longest may be this time period. I give you an example. Once I was broken down for a week, could not walk even. Then it was the end of the exams. So I thought, great, I went to ski. I'm happy that I was studying what I did, because otherwise I would have had ACL, I'm sure. Because when I went on the skis, I never got soreness during the whole week I was skiing. The problem is I never controlled my skis during the whole week. On any single curve, my skis were going apart. I was always surprised by what was happening. I was not controlling anything. I had no soreness. And I think that the more people are training, the less soreness they feel. And I'm not fully confident that they have no muscle damage at all. I'm not fully confident that everything is just perfect in them. What I'm aware is that for some of them, and it seems what we have seen now in our recent measurements may show this, is that they have some muscle damage, they have some inflammation, but their threshold is just higher up. They don't feel sore anymore. And then they feel superstar. And I think then the vigilance is not high enough. And what I would be interested in myself is that when you are in trails, you have all those endorphins going on. And I don't know how the endorphins makes that you feel or not soreness, because I asked a friend of mine before coming here, they said, no, you feel sore, but you don't feel precise soreness. You feel just sore a bit everywhere, and it goes and disappears, goes and disappears. What happens during trail? Because I think this is when you can't rely on the soreness, as it is clearly the case. You are not vigilant enough. You just think it works, and then you may be just damaging because your muscles are not holding your joints. What happens in trail?
I have no clue, but pain didn't disappear to me, for sure. Can tell. Okay. Yeah, tell me.
When you presented the data of the force velocity profile that Aki, I think, like, is it your PhD? Oh, sorry. You found like losses in speed after the, well, in velocity after the race, after the Marseille, right? And you found that only in men. Like, I was wondering how long did the race lasted? Like for the participants that 2 hours? Okay. Because the data we have that we collected for different studies, like for the UTMB or Red study, was not necessarily showing like losses in velocity after the exercise. So were rather losses in force, but velocity was not affected at all. Even they were better in velocity. And Fred's study, for example, was like 3 hours of low intensity running. it was mainly flat, yeah. Then but then in the UTMB was the same, and like was the force who was mainly affected and not the velocity. So this is why I was wondering, like, how an explanation for that, or from where that difference come, you know?
And if I can just add, in Renata's Kruger study that we published a couple of years ago, same thing for the prolonged exercise, there was no change in velocity. It was also force. Velocity only for the 10 minutes intense exercise and after the wind gate. So yeah.
Nice comments. I guess it may be also dependent on the ergometer we are using, because you are fully correct. Because when we are using this ergometer, you are lying in decubitus dorsal. So you're on your back, you are not thus supported your body weight, which means that this is favoring the fact to be reaching a bit more easily higher velocities of extension, okay? At least that requires you to be pushing as fast as you can without your body weight to force against at the beginning. And this may be why perhaps it showed some results we would not have at all in, like, let's say, squat jump. But anyway, yeah, and this is cycling for you. So the why you would have more in forces and not in velocities in cycling, I think it's all in terms of coordination. This ergometer is more like ballistic. I would not call cycling ballistic at all. And the thing is that on the ballistic, you just activate fully at first and then it goes. So it's just opposite, enfin, the completely different task. And it would be nice, in fact, to be checking on cycling versus ballistic movement to see the difference. But I can't answer you because we did not do both. No, but that's a good question. Yeah. No, in any case, every ergometer will be showing his own results. That's we know. What I like on this one, although I don't like pure concentric tests, because as I showed you, I don't believe in them really to show fatigue or to test the fatigue. What I like in this one is that you get then short push of time, which makes an additional constraint for you when you are fatigued to produce your multi-joint power or force.
Yeah, I guess at some point we'll have to compare, because if the conclusion we make about physiological mechanism depend on the way we are measuring it, then we have a problem. Yeah. So did you at least compare at rest, like people who have, for instance, a high velocity on the bike, for velocity test done on the bike, have also the highest velocity on your ergometer, at least at rest, or in fatigue condition if you have?
It's not my ergometer, it's Arnaud A's ergometer. So what I do is, as soon as I come back to Marseille, I'll ask him, because in the thousands of data he has, I'm sure he has that. And what I have seen in this ergometer is like people like Florent Manodou, for instance, is able to produce a push where everything is aligned. There is no deperdition of force in any other axis than the normal one. So it's also a difference with the cycling in the way that if you want to be efficient, you have really to concentrate on the normal force component. And on cycling, we know that it's also another strength, but it's more complicated. So I'm sure that Arnaud Ace has this. So if he's listening to, I'll ask him. And otherwise, when I come back, I'll send you back the information. It's pure concentric. Yeah.
Okay. Thank you very much, Caroline. We have to move on to the next and last presentation, Grégory.
Okay, it works. Good morning, everyone. Thanks a lot, Guy, for the opportunity to this talk. I will talk to you this morning about ascending speed and how to evaluate the ascending speed and use it for trail runners. So just a little bit of introduction. I'm Greg, I come from Perpignan. I also work in this environment, so it's pretty nice. I work in Font-Romeu. My laboratory is interdisciplinary laboratory performance, health, and mountain environment. We also have in Font-Romeu the National Altitude Training Center. So there is a lot of athletes and trail runners also come for training, altitude training. So it's a nice place, as you can see here, for some investigations. So we will start. First question, why is it important to quantify exercise intensity in endurance sports? Exercise intensity is very important in order to manage training load. You probably know all the literature on polarized training, and you have to polarize your training. Athletes polarize with nearly 80% of training in low intensity and 20% in high intensity. So you have to be precise in the quantification of exercise intensity. For that, you have to be precise too for the evaluation and the quantification of the exercise intensity at the both first and second ventilatory threshold, if you want to be precise in your training zone. What's this training zone and how to quantify this intensity? You have to, and you can use different methodology with 3 training zones, first, second, and third training zone. You can also use some methodology with 5 training zone of aerobic exercise and also use 7 training zone with the 6 and 7 zone, which represent anaerobic intensity. For quantification of this training zone, you can use different methodology. You probably know heart rate. Heart rate is very simple, but there is a lot of variation of heart rate of one day to the next one. Also, heart rate is not very easy to use when the duration of exercise is very short. When you have 30 seconds of sports, it's very, very difficult to use heart rate in order to quantify your exercise intensity. You also can use, and if you do some athletic sports, you also can use speed or velocity with the maximal aerobic speed, the percentage of maximal aerobic speed. This methodology is really reliable. It's accurate, but only during flat section. When you have slope, it does not work. And after, you probably know the power. The power is very used in cycling, and it arrived in trail running since years. The power is very reliable during running session. It's very simple because you have the power on your watch, so you run and you have the power. But the power is not very interesting when you are trail runners, because the power not work very well when you walk. And if you do some trail running, I think, like me, you walk on the UTMB, on the big slope, when the slope is very, very steep. So if you have an index who do not work when you walk, it's not the best way. If you see in mountain sports, in alpinism. If you take a guide, come from the Refuge du Goûter and you go to the mountain summit, the guide will say you, oh, we will go up at 400 meters per hour of speed from the Goûter to the summit. And we will make maybe 2 or 3 hours to reach the summit. So ascending speed is used in alpinism, is also used in ski mountaineering and vertical kilometers in trail running. This ascending speed is expressed in meter per hours, meter per minute, meter per seconds, as you want. And it depends on the speed, the linear speeds, and also of the angle of the slope. The ascending speed has been used by Monnet by the past. This study is very interesting, as you can see. And ascending speed has been used in order to predict performance in uphill section by Monnet. The race vertical speeds has been expressed here in meter vertical per second. So our ideas was, could ascending speed represent a reliable index in order to quantify exercise intensity in trail running? That's why that's our job and what we want to study, and we have studied in the past years. First of all, our first question was how to evaluate ascending speed. So we try to develop a specific test in laboratory condition, an incremental test in a constant slope of 25%, so quite steep. We have to regulate the increment with the ascending speed, and we increment this test with 100 meters per hour per minute. So we adjust the speed of the treadmill with the constant slope. And the question was, does this test is reliable to determine ascending speeds at first and second ventilatory dilation and also alveoli max, first one, and does this test reach to attempt maximal cardiorespiratory parameters? So we take a population of trailers, 20 trailers. They did 2 different tests, one incremental test as I described previously, and a second test with a limited time at 105% of maximal value obtained on the test one. This methodology has been used by some authors as shown in the past years. Our results, one on the progressivity of the test. What we want is that the test is very progressive in order to evaluate the first and second ventilatory threshold and also the maximal values. As you can see here on heart rate, ventilation, and also VO2, the test was very progressive with here the kinetic of heart rate, for example. So we could evaluate first and second ventilatory threshold and also maximal values with the plateau. Our data, so we have here the duration of plateau was nearly 1 minute. We have the maximal heart rate. We have the respiratory exchange ratio was over 1.1. And we have the rate perception of effort was over 8 on 10. So we have all maximal criteria was respect. And when we compare this data obtained on an incremental test with the data obtained on limited time, as you can see here, all the data was exactly the same. VO2 max, duration of plateau, heart rate, maximal heart rate, ventilation max, breath frequency, lactate, and the other values. All was the same. Only the duration of the test was different, but it's normal. So we conclude that this test that we name incremental allows, first one, the determination of ascending speed at VO2 max, the determination of ascending speed at first and second ventilatory threshold. What is very important is that in this test, subjects change their locomotion. They start by walking in the steep slope, and at one time, they start to run. And this was very progressive. But the big question is that, can we use ascending speed in all kinds of slopes? Because we previously said that ascending speeds really depend on the slope. So we did a second study where we evaluate the ascending speed in different kinds of slopes. We took 15 trailers and they did incremental tests on the flat at 15%, 25%, and 40% of slope. We measure all gas exchange, ascending speed, heart rate, etc. First of all, our results on the ascending speed in different kinds of slopes, 15%, 25%, and 40%, not on the flat because there is no ascending speed on the flat. But as you can see, there is a progressive increase in ascending speed. Normal, because you increase the exercise intensity between first, second ventilation and maximal exercise. Interestingly, we have the ascending speed on the 15% of slopes was lower than 25% and 40%. But what is quite interesting is that, as you can see here at first ventilatory threshold, the ascending speed of two range of slopes was similar between 25 and 40% of slopes. So we don't have any augmentation of ascending speed between this range of slopes. And it appears at first ventilatory threshold, at second ventilatory threshold, and at VO2 max. As you can see on this slide, when you have the VO2 max evaluation, we also show that VO2 max progressively increase with the slope from flat condition to 25% condition, but there is a stagnation of VO2 max between 25 to 40%. So that means that ascending speed could represent a nice index in order to quantify exercise intensity at submaximal and maximal exercise, and it works in a range of slopes between 25 to 40%. And that's quite good for us because it will say that on the field, when you are in the mountain, you can use ascending speed in order to quantify your exercise intensity when you are in this range of slopes. Moreover, it does not depend of the locomotion, because at VO2 max in 40% of slopes, all subjects walk, and at VO2 max in 25% of slopes, all subjects run. So it does not depend of your locomotion. That's very interesting when you are on the field, when you are in the race, in order to quantify your pace, your speed, your exercise intensity. Then we have another question, because all this BOSS study was in a laboratory condition. So what about the field condition? Because if we want that this test has been used, we have to develop also some field tests. We have to test that on field condition. You probably know all aerobic fitness tests realized in field condition, as Van Eval, Duc-Léger, Léger-Boucher. They all have the same methodology. You have some mark on a track. You have a soundtrack who give you the rhythm, and you have to be at the beep at the mark, and the speed progressively increase. We use this methodology in order to develop and to transfer our test to the field. But we have some questions. First, how to use incremental in field condition? Second, does incremental enough progressive in field condition? And could incremental allows to attain cardiorespiratory limit in field condition as we show it in laboratory condition? How to? We choose a track, constant slope of 30%. It's very easy for us because we are in a ski resort, so we take just the slope behind the lift. It's perfect, it's all the grass, and it's very constant. We calibrate the track with mark every 10 meters of denivellation, as you can see on the track with Van Eval test or Léger-Boucher. And then we create a specific soundtrack. For example, in our soundtrack, when you start the test at 500 meters per hour per minute, you have 72 seconds to go to do 10 meters of derivation. If you attempt 2000 meters per hour, you only have 17 seconds to do the same derivation, the same elevation. So the soundtrack will give you the rhythm, and you progressively increase the speed. So we use all the portable gas analyzer. We took 18 trailers, and our result was first on the maximality. We have exactly the same results that we obtain in laboratory condition with a respiratory exchange ratio over 1.1, with the heart rate max was like the theoretical heart rate, with the rate perception of effort over 8, and the lactate max over 8 millimole per liters. We arrived to determine the under maximal transition zones in all subjects mainly because our test was very progressive. As you can see here, our test fit with a linear increase of VO2 max. So it's very progressive. Also in field condition, because in field condition, it's more difficult. On the laboratory condition, it's perfect. You have the treadmill and the guys run at the speed of the treadmill. But in field condition, that was not easy. And as you can see here, this linear relation was nearly the same between laboratory condition and field condition. So it works well. So in field condition, incremental allows, if you don't have any material, if you only have marks and soundtrack, could evaluate the maximal aerobic aptitude, maximal ascending speed, specifically for trailers. And specifically for trailers because it's in the slope and it does not depend on the locomotion, walking or running. And if you have portable gas exchange material, you can evaluate also maximal ascending speed, but also transition zone and ascending speed at transition zone. So you can evaluate better the race pace for the trailer, but also you can determine exercise intensity training specific for trailers when you are on the slope. Then we have another question. What is the limited time of ascending speed? Because another part of field test are all the limited time or all-out test, as you probably know, as Cooper test, half Cooper, Astron, alpha Astron, etc., etc. This test, this limited time test, estimates maximal aerobic speed. But what is the limited time at maximal ascending speed? So we took a nice population of students, of sports students, of 35 trailers. They did two kinds of tests. All subjects did two kinds of tests. First part of the test on the flat. First test, Van Eval test. Classic. We evaluate maximal ascending, maximal aerobic speed. 2 days after, they perform a rectangular test at 100% of this maximal aerobic speed previously evaluated. And we see the time that they maintain their maximal aerobic speed. 2 days after, they perform an all-out test of 6 minutes, and we measure the maximal aerobic speed. Normally, this one will be the same as this one, normally. Then, we did field test in slop conditions. So, first of all, subjects perform an increment trial in field condition with the evaluation of maximal ascending speed. 2 days after, they did a rectangular test on the same track at 100% of maximal ascending speed. We showed that. And 2 days after, they performed an all-out test at this time measured during rectangular test. And we measure maximal ascending speed. Our hypothesis was that this one will be the same as this one. Our results. First, on incremental test, on the flat, the Van Eval, you have the speed, the mean speed of our group. And here, in Slop condition, you have the maximal ascending speed of our group. Then, on the rectangular test, first, on the flat condition, subjects maintain their maximal aerobic speed 5 minutes 46 seconds. So it's quite close to 6 minutes. That's nice because when you do a 6-minute all-out test, generally it's quite close to your maximal aerobic speed. And interestingly, when the man perform to maintain this maximal ascending speed on the slopes, subjects only maintain 3 minutes 51 seconds. So for the last test, for the all-out test, we choose to realize on the flat section the 6-minute test, and 3 minutes 51 seconds, we choose to realize a 4 minutes all-out test in Slop condition. Our results was quite nice because in this all-out test, in 6 minutes in 5 conditions, subjects have exactly the same maximal aerobic speed that the incremental test. And on the Slop condition, it was the same. Subjects on the 4 minutes all-out test have exactly the same maximal ascending speed that we observe in incremental test. So our conclusion was that limited time of ascending speed, of maximal ascending speed, was quite near 4 minutes, and that's a big difference with the flat condition. And secondly, a 4-minute all-out test on a slope, in a slope of 25 to 40% could easily assess the ascending speed at VO2 max. So that's very useful for the coach, because if you have a constant slope, you can do this test to your trailer and do an all-out test during 4 minutes, and you can assess the maximal ascending speed very easily. And after, you could use this value for the race paces, or in order to quantify the intensity during the training session, as you can do on a field track. So, some key points to retain of this topic. First, ascending speed could represent a reliable index in order to quantify exercise intensity in trail running and whatever the locomotion. And that's very important, walking or running. Ascending speed is usable between 25 to 40% of slopes. And that's nice because when you go on a ski resort, it's red or black track. Incremental could represent a good test in order to evaluate ascending speed at maximal and submaximal intensities. Incremental could be used in field condition. And a 4-minute all-out test could be used to evaluate ascending speed, maximal ascending speed in field condition. So thank you. Thanks a lot for that. I really want to thank also some partners who are involved in this all this project, and also collaborators, students, or colleagues who will take part of that. Thank you. Thanks.
Great, thank you very much, Igori, for this interesting presentation. Jamie, are you still with us? Went back to sleep. No, here he is, not even sleeping. Hey. I hope you were able to follow the other two presentations. If you have any question, of course, feel free to ask. It is 11:30, but we'll take a few questions anyway. So I actually have some, but if you have, go ahead in the room, or Jamie. Yes.
Thank you very much for your brilliant presentation. It was very interesting. And you said multiple times that the incremental test can be used slopes between 25 and 40%. And you were pretty confident in that. And I was just wondering what happens with poles, because we use poles, not these slopes usually. And
yeah, we did some tests with the poles on this kind of test, and what we observe is that performance is better, and nearly there is 100 meters per hour higher with the poles. So you increase your performance of 1 step on the incrementals test.
And how about VO2 max?
What?
VO2 max.
VO2 max do not increase significatively, but on a rectangular test, the mean VO2 was increased during all the tests, but not VO2 max, not significantly.
But still, VO2 was increased, so meaning that if you train with poles, it could be a good idea including during interval training.
But when we passed subject, it was subject that were trained with poles, because it was ski mountaineering runners, or also cross-country skiing runners.
Yeah. That was actually also one of my questions, and on that as a follow-up, when you said, for instance, that you can test doing just a 4 minutes all-out test, I was just curious about you said it's experienced runners, so they know about pacing. But if you have, it's true, not only in uphill, of course, but for any rectangular test, if you start too fast, what happens? So can you comment on that?
That the limit of all-out test, because we did a rectangular test where there is a soundtrack for give us the pace. So on the rectangular test at 100% of VO2 max on flat or slope, they don't have to choose their rhythm, because we give it the rhythm with the soundtrack. So there is no limits. But on all-out tests, they did what they want. And I totally agree with you. When you don't have experts in aerobic sports, subjects always go faster at the beginning, and after speed very decrease all around the test. So it's a kind of test could be used only with experimental with athletes who are was some experimentation about the pace.
Yeah, this is critical because if you want to do an incremental, a true incremental test in uphill, I think you showed data showing that it lasted 15 minutes, and not everyone can have a 15 minutes with a regular slope. It's almost impossible here to have that.
Yeah.
And I was actually curious when you said it's very easy to find a constant slope.
Still resolve.
Yeah, but still, the slopes are generally like could be similar, but to stay very constant for 15 minutes, it's pretty rare, even in Font-Romeu, I guess.
You have to be constant between 25 to 40% of slopes, because if the slopes vary between this range of slopes, it could work.
Yeah, but then you need to adjust the beeps.
No, because you adjust your biomechanic, and if you have a little so if you have 25% of slopes, you will run, and after, when you go on the 40% of slope, you will walk.
Okay, I got it.
And you will adjust your biomechanic in order to keep the pace and the rhythm of ascending speed.
And sorry, and then Caroline, but then last question for me. You said 25 to 40 because this is what you tested, but are you sure it cannot be from 20 to more, maybe?
Maybe I hope the range will be greater, but I don't think that it will work, because it's very, very strict. Maybe you can have a little bit lower with 20, but we only test between 25 to 40. But it's But it's a big range of slopes, 25 to 40.
Thanks, Craig, for a really nice presentation. I could not perform this, but I'm really interested in your results. I would have two questions. When you make this all-out test, what advices do you give to those who are not fully elite traders, the way they should warm up? Because students may be asking such questions.
We did not do some really recommendation, but the subject performed the rectangular test before the all-out test. So 2 days before. So they had an idea of the rhythm that they have to keep during this period. So it's we don't need to say to be prudent at the beginning of the test, because they perform the rectangle.
Yeah, I was speaking about warm-up.
About warm-up. Oh, they did warm-up before.
But it's not controlled.
Yeah, 15 minutes of warm-up with some acceleration of between 10 and 15 seconds at the end of the warm-up, in order to be fit with as if it was the beginning of the competition. So we control the warm-up on the rectangular and on the all-out test.
Thanks. And I was really interested by the way you got similar physiological response at 25 and 40% independently of the locomotion. This is great. But so it seems to look like there would be the constraints close enough so that you are recruiting, for instance, the gluteus maximus, or more the rectus femoris, or more the hamstring muscles, in order to either when you are walking or running to face such slopes. And this would lead then to similar physiological response. Did you intend, or did you make already controls in terms of EMG?
No.
What's going on to show those similarities?
No, we did not evaluate the EMG on that. We evaluate the transition zone between walking and running, because in our mind we think that all subjects will have a transition between walking and running at the same moment. For example, at 70% of VO2 max. That was, I don't know why, but that was in our mind. But it's not that, because all the transition depend of the elastic recall, depend of the biomechanic adaptation. If they are more strong on the quadriceps, they will walk a little bit. If they are a good elastic recall, they will run before, because they will use this elastic recall. So there is no link with the transition and the physiological adaptation, but we did not measure the EMG. But it could be really
It would be nice. And differences between men and women could be also interesting.
Yeah, also. But we don't have here, we only have men in our study. Sorry, I apologize.
Thank you, Greg. Yeah, maybe the last one. We're already late.
You showed that, well, thank you, first of all, for the presentation. I'm a little nervous today. Yeah. No, I know.
Be careful.
You showed that VO2 max was greater at 25 or 40 compared to 15 and 10. So I was wondering, what did you find in terms of the VO2 at VT1 and VT2? Was it also greater at those higher slopes? Which would then mean that you would, like, if you want to maybe, I'm wondering, and this is a question open for you, I guess, if this VT1 is greater when you are going at 25 to 40%, would you then train even at low intensity in a higher slope to get maybe more stimulus from this training or something like that?
I did not present the result, but we have a very linear distribution of VO2 and evolution of VO2 and ascending speed. So whatever the locomotion is very, very linear. So you have a linear relation between these both parameters.
Did you expect such a difference with slope?
What?
Did you expect such a difference with slope, that the higher VO2 max at 40% or and 25%? Because even between flat and moderate slope, it's not that obvious. Sometimes it's sometimes.
Yeah, the literature is very different on that, but I think there is no difference between 25 and 40% of slopes on our group. Also because it's athletes who are very involved in mountain. So they are very efficient on walking part. And they can walk very, very, very fast also. They can run and walk very, very fast.
So how do you explain this higher VO2 max? Sorry, I said it was the last. More like the glutes?
Maybe. The higher VO2 max on 25% of slope, because you run and maybe you use a little bit.
So you compared with 15%, right, or 10%? I can't remember.
What?
The lowest slope was 15.
15.
And you also run.
Yeah.
Very different.
You run, but the energetic cost is greater in 25% of slope. So no.
It's interesting stuff.
Yeah.
For sure. Okay, so we'll stop here. Thank you everyone for being here. Thank you again to the three speakers and again, especially to Jamie.